And first speaker is Joel Lemon, and their title is The Surprising Creativity of Digital Evolution.
Hello. So my name is Joel Lemon, and I'll be talking about this paper, The Surprising Creativity of Digital Evolution, a collection of anecdotes from the evolutionary computation and ALIFE research communities. So, as this title suggests, this is a paper that collects stories from researchers about when digital evolution has surprised them. And I want to note that Dule Mistic submitted the abstract to this conference, and we wanted to hear it presented, but I'm doing it on his behalf. So I'm Joel. Jeff Kuhn also was an organizer of this paper with Dule, and this was a collaboration, a big effort with 50 other authors. Yeah, so kind of fun to be on this paper with so many really seminal researchers, and so it's kind of interesting work to collect all these stories from people who have been surprised by their algorithms. So I think I'm in a community here where I don't have to do too much work to convince you that natural evolution is a creative process. Here I have some of the some sort of surprising adaptations that evolution produced. The bombardier beetle, which kind of engages in chemical warfare. We have an acoustic beacon plant that attracts bats, and there's a parasite here that infects a grasshopper to get it to commit suicide as part of the parasite's life cycle. So certainly devious, surprising sort of innovations that if a human invented these things, we certainly would say that was a creative thing to do. And this kind of ties into Ken Stanley's keynotes earlier this week, arguing that natural evolution is open-ended and very, very creative. So for those of us who work in digital evolution, we're interested in evolution in a different substrate, the digital substrate, where we work with models like Vita on the left, where you have evolving computer programs. On the right, we have seminal work from Carl Sims on evolving virtual creatures. We're familiar that sometimes our algorithms do crazy and surprising things. And so we might have this opinion that digital evolution is creative. We've experienced it ourselves, but when we go to talk to other people outside of our community, we often get sort of some pushback on this. Maybe some of us have experienced this in the review process. Groups are like, no, everything is programmed, so what comes out can only be a function of what's put in, predictable, there's nothing that can teach us about evolution in general. And it's been kind of a frustrating experience because from our perspective, we've actually experienced the creativity, the surprise of it, the subjective surprise. We have many anecdotes that maybe we've experienced or others have experienced about how evolution has surprised us. It undermines our fitness functions, comes up with a solution that we didn't realize was possible. And these stories are often told at conferences over beers and not actually published because they don't really fit the scientific narrative. So this is what Jeff Dule and I set off to collect and try to publish. We set off what we thought was going to be just a 4-month sort of endeavor, and it's been about 2 years now. And finally, we're kind of nearing the end of this process. So some of the backstory is actually a work that's been, I think, about more than 10 years in the making. So I wasn't present at this conversation that happened a long time ago. I think the idea actually came from Elizabeth Ostrowski when she was at MSU. The idea to actually start to collect these stories because they're so kind of inspirational and interesting. And the inspiration for the process by which we kind of crowdsourced this paper came from Tim Taylor, who had a crowdsourced paper on artificial life on the web that was really interesting, and it was sort of like, oh, we can do this too. And so finally, we decided to execute on this and set out a call for anecdotes on evolutionary surprise for those in this community through the mailing list that we were familiar with. And the idea was that if you submitted an anecdote and it was accepted to be a part of the paper, then you become a co-author on the work. So kind of a natural incentive to get everyone to submit their work. So we curated, edited, and categorized this into 4 gross categories. One we called selection gone wild. This is the idea of when you have an idea for what you want and you think you've specified it mathematically, but it turns out that evolution is going to prove you wrong. So I'll just go through like one example of each of these categories. There's many more examples in the paper. So Peter Prasad, in 2008, had a virtual creature set up, trying to get virtual creatures to jump. And so he was thinking, one way to measure jumping is something related to how high a block that was initially on the ground goes during the fitness evaluation. And so intuitively, it seems like it has something to do with jumping, and then evolution creates this crazy morphology where you have this big pogo stick thing that's on the ground and uses a lot of torsion to kind of flip itself, this block up to the top. So evolution's like, this is what you asked me to do. This is, I'm actually jumping in the way that we wanted to, but of course, this is more what Peter wanted at the time. There's also a lot of situations where evolution is going to debug our simulation. So we're pretty sure that our simulator works. And then we discover something like this. So this is an example from recent work using an evolution strategy to evolve an Atari player, and discovered a latent bug in the game Qbert that had been sitting there for about 30 years, where you can rack up a lot of points without actually doing anything. Sometimes evolution will surprise us by exceeding our expectations, by showing us solutions that we didn't realize were actually possible within the space. So this is an example of a 6-legged robot. The experimenters asked the robot to generate a diversity of walking behaviors using different combinations of legs on the ground. And you have 1 leg on the ground, 2 legs on the ground, and there's one niche for 0 legs on the ground, which seems like, well, you can't walk with 0 legs. But evolution said, no, I'm just going to flip on my back and sort of like wiggle on my elbows. So, didn't see that one coming. And other times we get unexpected convergence with biology. So we have this digital substrate, which is much different than the biological substrate, yet sometimes we'll see similar sorts of phenomena, which is something that we might expect, but also is kind of nice when it happens. So one example of this is Tom Ray's work with Tierra, where one of the initial runs of the system produced parasites and hyperparasites. So something we see in biological ecologies, and it was really interesting that he didn't directly expect that to happen in the system. So to conclude, I think it's nice that we can preserve some of these classic important stories for the future. It's hard to find room for this sort of subjective sort of experience in the scientific publishing process, which I think is really frustrating, because this is ultimately something that is worth studying. And I hope that this helps to show that digital evolution is routinely creative, and we can use this as a resource to rebut maybe antagonistic reviewers who might be difficult to otherwise convince. So thanks again to all the co-authors, and the full paper, journal papers on archive, and we're still working to publish it in another venue. So thank you.
Any questions or comments? Yes.
Thanks. And I guess I speak for everyone. We love those stories, and indeed we tell them over beer. I'm wondering if there is value. Do you see value in sharing those stories? Basically, negative results are really interesting. We usually don't read those in journals because they're not as impressive as the positive ones. Maybe that would be a good thing to organize. Maybe an archive of negative results.
That's certainly an interesting idea, and I think some people, throughout the years have recognized that there's this hole in the scientific publishing process where we always present this polished story of, I, the genius, had this one hypothesis, and I ran one experiment, and it just worked. I think many of us know that's, not really the way that science works. So I agree that it'd be nice if there's a way to kind of tell the whole story. And, if you have ideas for how to make such a venue, that'd be kind of interesting to think about. I agree.
Okay.
What is the conclusion?
Right. Sam. Yes.
Here. Are these really negative results?
I think from one viewing, they might be, and that usually the researchers were in pursuit of a different research question. So yeah, I agree. Like I think it's an issue of perspective, because from one lens, it didn't work the way you expected, and that could be kind of negative. But ultimately, it's a very, very interesting phenomenon in its own right, and deserving of further study. So I think it's not necessarily negative.
Okay. Any other questions?
Thank you very much. So creativity is in the eye of the observer. But this idea could be quantified and could be evolution for being creative. If we could make a selection criterion for the evolutionary process, we could make new evolutionary methods that are innately creative because you want them to.
Yeah, it's an interesting idea. How is it that we explicitly drive evolution towards creativity? I think some of those same questions are explored in like the idea of open-ended evolution, or algorithms like knowledge search, which I was involved with, where there's something called surprise search, which is also motivated by similar rationale. So I think it's definitely worth considering, and it would be very fun to see a truly sort of profoundly creative algorithm.
Okay, thank you very much. And the next talk is neuronal variation as a cognitive evolutionary adaptation. The speaker is Jory Jory Jorsler.
Hi, my name is Jory. I'm a postdoc at MSU. I'm here to tell you a little bit about this fun little project we started recently, very recently. I have a little bit of preliminary data to keep it off. So this is not the clicker. This is the clicker. So you're all familiar with the abuse of the colon in scientific literature, right? So mine looks like this. So this is a proposal for how to think about noise across cognition and machine learning, and a bit of preliminary data. Okay, so when I say noise and cognition, what am I talking about? So this is data presented this year by Emily Magavicius because of a tool they're making. Okay, so I'll tell you a bit about that. On the y-axis is neurons, x-axis is time, and z-axis, which is the black bones, is signal activation of the neurons themselves. So what they're trying to do is find the signals through the data, through this high-dimensional and noisy data. So noise is something that neuroscientists have to deal with. However, this is a highly contentious topic. Depending who you ask, depending which neuroscientist you ask, you say, is there neuronal variation? They'll say yes. Maybe this one, no. It's highly contentious. However, this is exactly the noise I'm talking about. So, as it's contentious, where does this noise come from? It might come from a variety of places, all the way down to the chemical stochasticity, right? The ion channels, the cell bodies, dendrites, all the way up to synapses. My favorite hypothesis is that it's a result of an incomplete observation of the whole system. Right? If you can only see a little bit of part of it, just like the what can neuroscience learn about CPUs approach, then it looks like noise. So when I talk about noise in machine learning, what am I talking about? So we're familiar with genetic algorithms. Noise is used as primarily search, or if you're doing more like generative art, this is used to help make surprise, right? More words to mean sort of the same thing. And these are all sort of lumped into different types of regularizations or methods of selection, all based on stochastic methods. So like OpenAI's ES, lexicon selection, these are all different types of stochastic searches. And they help you avoid overfitting, right? So, but what I'm talking about is really noise at the cognitive substrate level. So let's take a look at everybody's favorite neighborhood cognitive substrate, the artificial neural network. And let me show you different types of noise here and what I'm talking about. So you can put noise on the input nodes, right? And this is equivalent to generating more data for your algorithm to train on. You could put noise on the outputs. This is equivalent to like faulty servos and simulating real-world environments. Your algorithm may become robust to this sort of noisy output. But what I'm talking about is really noise on the hidden nodes, right? This internal cognition, the algorithms in here. And in our substrates, we actually have recursion in between and back and through the hidden layers. So this becomes even more of an issue. So how do you design algorithms such that it can cope with the assumption of faulty components within the algorithm substrate itself? And what does that mean? So in what cases is this kind of noise beneficial? All right, this is sort of the thought experiment part. Let's assume you have a maze here, the agent is the triangle, and it is trying to find the green dot. All right. Now, you might say, okay, one end of the spectrum of using noise, you have absolutely no noise. Right? This is either hand-designed or an evolved deterministic algorithm, completely replicable, follows the same path every time. Wall following is a perfectly reasonable answer here. However, no matter what algorithm you design, no matter how smart you think you are, there's always going to be some environment that you won't be able to solve. Right? This is the problem with deterministic strategies. On the other end of the scale, you have complete noise, and if it weren't for the heat death of the universe, I would guarantee it would be able to solve every problem. However, there are usually resource constraints or environmental constraints or what have you, which makes this impractical. And then somewhere in the middle is a strategy that can use determinism or be able to pick up on regularities of the environment and exploit them, but use a little bit of randomness to bump itself in and out of different attractors in behavioral or environmental space. Right? And so what is the point here? So that some problems require lots of deterministic exploitation, and some problems require a lot of exploration. Right? And perhaps evolution may select for just the right amount of noise to balance between exploration and exploitation, given the different types of environments. So, toward this end, I have a bit of preliminary work that I have been evolving in a digital system. I'll breeze over the details. I use the MABE framework, which you can learn about later. You can attend our Hinz's talk. And the whole point of this thing is to make agent-based evolution a breeze to do, and analysis and implement. And so I have 3 different environments I tried. One is a block-catching environment, originally proposed by Randy Beer. The agent is on the bottom, can only shift left or right, must catch a falling block. It actually has to figure out what classes of blocks to catch, big, small, fast, slow, this sort of thing. The second environment is path following. It can't see the path, and it's rewarded through selection and reproduction for eating the black things along the path, but it can see the road signs. Now, these road signs are automatically generated at the beginning of every lifetime, but they're random, and the meanings are randomly assigned. However, the world is self-consistent, so the agent has to do a bit of exploration at the beginning of its life, and then solve this thing. All right, and then the third and final one is a binary maze task. It has to solve this maze, and then at every doorway, there's a little bit of information it might be able to use if it were paying attention to solve the very next door. So then getting onto the data for these, here's the data for the maze, or the block catching task. And the important bit here is that the red line is the base assumption of no noise. All right? This is generational time, or evolutionary time, line of descent, average fitness. And we compare no noise with the black line, which is the best of all the different small amount of noise parameters. And to find that noise just really doesn't help here. I suspect it's because the agent really has to solve this thing perfectly, or it doesn't at all. The second task, the path following task, right, there are some extra lines here, but again, the red is the baseline, right? Here the x-axis is the different types of noise that I tried, increasing in noise probability of how faulty this counter substrate is, and the other lines are different types of noise on the different types of sensors, like input and output and hidden states. All right, versus the black line, which is across all nodes everywhere. And the black line is sort of the hypothesis. All right, and this is the final one that says maybe there's something interesting going on, where there's the black line that shows a little bit of bump for a very small amount of noise way up in the corner. Right? Obviously, there needs to be more replicates, but perhaps there's something interesting going on here. So future work is we'll make a more specifically designed environment to test the hypothesis. So in summary, evolution performs better in some environments with small cognitive noise. This hints that perhaps spatial exploration, like a 3D complex world, benefits from small cognitive noise. So I'd like to thank the rest of my lab, who makes it a great place to work, and Beacon Center for Study of Evolution, and our Computational Center. Thank you.
Any questions? Yes.
So while there clearly are many discussions about the role of noise and when biology just has to live with it, there are also very beautiful examples, quite a number by now in neuroscience, where we know that noise is really used and absolutely necessary to make things function, like increasing the dynamic range of perception of neurons by having different functions of otherwise identical ion channels, and there are very, very good models for this. The idea of growth cones having random exploration of molecular dynamics and so forth. Have you tried, so basically this idea that you're using to titrate in noise to see when you have the optimum balance to make this thing function. Could you use this to use those established examples where noise is known to be required and see if they are optimal solutions?
Could we go the other way around? Yes, we totally could. This is what I presented as one method for experimental validation, right, to investigate this problem. We could totally do it the other way. I think it would require a bit more experimental setup on our part.
Yeah.
Yeah, so the systems you are using, they are all Markovian, right? And you know that for a Markov system, the optimal policy is deterministic, right? So it's not really a surprise that the solution, I mean, with the evolutionary algorithm, you find a solution, right, to the MVP, which is the best one, is deterministic.
No, the worlds are not deterministic. The problems are not deterministic, so we can solve this using a variety of substrates. We just happen to be using Markovian substrates.
Yes, but I was arguing that you would need to use potentially a different substrate in order to show that this is...
uniform across all substrates. Yes, we can totally do that. I think
Like
that's an excellent extension.
Like MVP type of thing, right?
Yes, yes. And the point of our framework is we can swap out all the different cognitive substrates. So I think that will be a good thing to do later on.
Short question.
So actually, you talked about noise as something kind of parameterizing. Thank you very much. Parameterizing exploration versus exploitation, managing the balance. Usually, in the evolutionary computation community, we see, or at least I do, selection pressure managing that too, and maybe mutation strength. Care to comment on that?
Yeah, so mutation, in one respect, is a type of stochastic search, right? And so I would lump that in with the stochastic search of finding the algorithm. Whereas what I was talking about is really the behavioral level of the operational noise of the network itself during operation.
And what about selection pressure during the evolutionary process? Like being more selective, or more elitist, or less elitist, allowing for exploration? What do you think about that?
I think that's another kind of selection mechanism that, yes, we could try other selection mechanisms, but what we're curious about is if evolution chooses different types of noise within the network, optimizes, let's say, not mutation rate, but noise rate of the components during their function.
Okay, so at the level of one network or one individual and not at the level of the evolutionary process. Okay.
Right.
Okay, thank you so much. Next topic is seeking open-ended evolution in swarm chemistry, analyzing long-term dynamics by your automated object, the harvesting. The speaker is Hiroki. Please.
Thank you, Izuka. So sorry for the not very long talk. I was not expecting to be selected for the lightning talk. As you see, 2 is there. So this is the sequel, and everybody knows the sequel is always over budget, and less interesting, more boring. But I hope that not many of you have read my first paper, so I think it's going to be okay. So once upon a time in Paris, I published 2 papers. One at the IEEE ALIFE, that was in Paris back in 2011. The other is also in the same year. It was a poster at ECAL. And what we did was to use the swarm chemistry to make evolvable for those who don't know swarm chemistry, it's basically the multiple species mixture of the Craig Reynolds voice model. And then you can train or create design of how to mix different types to create some self-organizing patterns. And in this evolutionary version, the information about the recipes are carried by each particle. And then when particles collide to each other, one of them will be selected as a winner or the source, and then the other side is going to receive the information. So that creates a very basic physics law where there is absolutely no global fitness function. We don't know what's going to happen, but you can still create the evolution pattern like this. So back then we thought, oh, this is a great example of the potentially open-ended evolution, and then I stopped working this. But now, many years later, I get promoted, so now this is the time to come back to the really important stuff. So is it truly open-ended? So we revisited this evolutionary swarm chemistry model to do 2 things. So one is to simulate much longer. I have seen a couple of the talks in this conference also doing the same thing. We should look much longer evolutionary dynamics to see what is going to happen after you finish the simulation to publish a paper, right? And also, in order to do that, I definitely needed to have some kind of automated process because I don't want to keep seeing that for the entire 24 hours. So we definitely need to have automated observation process, which actually nicely resonates to Dave Ackley's talk that he gave yesterday at the open-ended evolution workshop. So these are two things we did. So the automated object harvesting in the swarm K-stream model goes like this. This is using the image processing. So here is the configuration of the one particular snapshot of the simulation process. You first apply the blurring so that you can actually create a contiguous area, and then you can binarize, and then dilate a little bit so that you can also include some peripheral patterns when you crop the patterns. From here, you can extract these objects automatically from each and every configuration. And then, once you get each of the objects, you can measure a bunch of stuff. You apply the same process to create a spatial masking pattern, and then you get this pattern extracted from the system. You can rotate it so that it can fit in the rectangular pattern, and then you can measure height and width. This captures some basic information about its morphology. You can also measure some other stuff, such as the color entropy, how many different types are included. So this is all automatic. Okay. And also, we introduced some environmental perturbation here and there. And in this paper, we tried two different versions of environmental perturbation. One is to the short, moderate version. This means that once in a while, the underlying physics law changes from the default mode to something totally different in one of the two sides of space, either left or right, randomly chosen. The other one is much more severe, that such kind of environmental perturbation that persists much longer, 10 times longer. This was not tried before. So we just want to see how the evolution process is going to be influenced by those two different kinds of environments. So here are some boring plots coming from the automated object tracking process. Here we plot the bounding box width, bounding box area. So in the moderate environmental perturbation condition, they generally go higher over the very long period of time. So this is a kind of good news. So the evolution actually tends to create larger and larger and larger objects for some reason. Okay. However, this also depends on the severity of perturbations. If you try a much severer environment, this trend does not occur. Okay. And other examples. So these are the color density. So number of colors, color entropy in both the moderate and the severe environment. The left one is moderate. The right plots are the severe ones. The severe environment actually increases color entropy. So that means that depending on the environment, the patterns, nature, size, and the complexity of the mixture of types actually get changing. So that means that this is a signature of adaptation, even though we are not using any fitness function.